Thank you, Gyanam. Lovely being here. This is unfortunately the first lecture of the seminar that I'm actually able to attend, and it's probably the worst one so far. So I hope to stay up in future ones and attend the lovely series. That it's some really exciting talks in the series. Um, but yes, so I will be talking about MCMC importance sampling via Moreau-Yosida envelopes. So like Wanyang said, this is sort of in the intersection of sampling, importance sampling, MCMC sampling, and then also optimization. So just to set some context first, the project itself is led by my PhD student, Apratim Shukla. He's should be on his way to graduating. He's finishing his 4th year, should be graduating next year, hopefully on track. And then this is in collaboration with Professor Eric Chi, who's at Rice. And the collaboration itself was pretty cool because what happened was that there was a call for an internal grant between IIT Kanpur and Rice, and it was just competitive between our two schools. And we sort of knew each other, but not really, had never really worked or even thought of working. But because it was just this grant that was only between our very two small universities, we thought we'll try and write something up and started discussions. And this is, the first work that's come out of this a very promising collaboration. So pretty cool that we sort of just tried something and it led to some nice ideas that we think. So I'm just going to set some context on what is going to be the focus of the talk. Because this is, a Monte Carlo seminar series, I'm going to assume there's a reasonable amount of knowledge base in general Monte Carlo methods, but I'll still be slightly pedagogical at some places. So at the outset, what we're interested in doing is there's a distribution with density pi, and pi is of the form e to the minus psi of x. So this is just the way I will be representing the density. And psi of x is the part of the density that I will be concentrating on. And what I'm interested in is estimating characteristics of pi. So for example, I could be interested in the mean of the density pi. And I'll denote that object of interest as theta. So theta is an expectation of interest for us. This is like the overarching focus, and then the restrictive focus is that we considering target distributions pi that are within the following restrictive class. They're log concave, which means psi of x is convex. They could be non-differentiable, which means psi of x is non-differentiable, or they could be such that the gradient of psi of x is not Lipschitz. So it has maybe very fast decaying tails, or it is not differentiable. So these are the class of distributions we're interested in. And a lot of what I say will be restricted to these class. Okay. And just again to set the premise is typically what is done when we have a target density of this form of interest is we run a Markov chain Monte Carlo algorithm and we obtain samples from pi, and then we use sample statistics to estimate features and characteristics about pi. What is their typical go-to default algorithm we might want to implement if we have no other things that are at our disposal is the Metropolis-Hastings algorithm, which updates itself in the following way. So given at a certain time in the Markov chain, I am at at state xk, which is small x. I obtain the next iteration by the following paradigm. I draw a uniform, I keep it in my pocket, but then independent of that, more importantly, I draw my proposal from a proposal distribution or kernel, which I encode with density q. Okay, so it's a conditional distribution essentially given a particular value of x. And I set with some probability alpha, which is the Metropolis-Hastings probability, I set the next iterate xk plus 1 to be equal to y. And here I just do something convenient is I just write pi y by pi x in our sort of usual the notation that we set up before as e to the power minus psi y plus psi of x, right? So the constants cancel out. And with the rest of the probability, I stay where I am. And this is what we can run in any given problem if I have pi up to proportionality. Of course, the the effectiveness of a Metropolis-Hastings algorithm is almost completely determined by the choice part proposal. And common proposals and sort of the default is often the random walk proposal, where Q is a standard Gaussian, a Gaussian centered at X with some variance H that we might tune. And another is the popular Mala algorithm, or the Metropolis adjusted Langevin algorithm, where the mean of the proposal is augmented or shifted according to this gradient of log of pi of X. Now, just to sort of reiterate my notation, gradient of log of pi of X is then nothing but the negative of the gradient of psi of X, right? So this is just to reiterate my notation. Okay, and then what we typically do in an MCMC setup is we run our Markov chain, and then once we run this, our samples though are often correlated, which imply that if I take estimates of my actual expectations, which could be sample means, then the variance of those sample means can be quite inflated because of the correlation in my Markov chains. And so very highly correlated Markov chains can yield not very good estimation quality because of the high variance in the estimators. And so typically, as a practitioner, maybe what one might want to do is reduce the variance in estimation of the posterior estimates by a couple of different methods. And some of these methods, sort of default methods, would be to maybe use a better Markov kernel, a Markov chain. And a way to do that is to employ gradient-based proposals. So I'm going to choose Q such that it uses gradients in an informed way to build better proposals. And another way to reduce the variance is possibly to use important sampling, which is the idea that I sample from a different distribution, and then I correct for the fact that I've not exactly sampled from the right distribution. And so what I'll do in the next couple of minutes is break down the gradient-based proposals and important sampling and what they really mean in sort of helping us through this problem. Okay. So first I'll look at gradient-based proposals. So just to give us an understanding of the impact and utility of gradient-based proposals is, let's assume I have a Gaussian target, normal 0, 1 target, that's given in this black density. And I'm currently at this red dot X. So my current state of the Markov chain is -3. And a random walk proposal is then centered around -3 because it's centered around exactly where I am. But then a Mala proposal takes the sign of the gradient of the log at this place. So the gradient is a positive number. And so it sort of shifts it a little bit towards the direction of the gradient. And so the Mala proposal is basically slightly more shifted towards the mode. That's going to encourage larger jumps, which is going to encourage faster, possibly faster movement in my space. And so this is sort of a demonstrative or visualization of why gradient-based proposals can be fairly effective. So they're utilizing more information in the proposal, can then improve, lead to bigger jumps. And then there's multiple different types of algorithms, like the Mala algorithm, HMC, Parker's algorithm, and then Riemannian manifold versions of these algorithms that actually look at possibly higher order terms rather than just the gradients. So this slide is sort of like the main pros of gradient-based methods. But then there's some cons as well. So for example, if I look at the target, pi of X is proportional to e to the power minus x to the power 4, which is called the super Gaussian target. Then the random walk at the same point is certainly still centered at where we were before. But because of how massive the gradient is at this point, the Mala proposal is actually centered around 70 or 80. So it's completely out of the plot right now. And that's because this particular target over here is not gradient Lipschitz. And so it doesn't have well-behaved gradients. The gradient doesn't really scale linearly. It scales cubically in X. And that makes Mala fairly ineffective in this example, especially if you don't choose your starting value well enough. And then naturally, another thing to keep in mind is that Mala requires a differentiable target density. And so these two are going to be the two cases that we are going to focus on, is when we don't have well-behaved gradients or our target density is possibly not differentiable everywhere. So choosing a better proposal and gradients in our proposal is one way of building effective sampling strategies. And then another is to do something different, is to sample from a different distribution and then employ importance sampling. So I'll talk about that for a second. So what is importance sampling? Well, what we do is we identify another distribution with density small g, and we're going to run a Markov chain YTs that is going to sample from G. And at that point, I can define unnormalized weights, which is the W's, which is the ratio of the unnormalized target divided by possibly normalized or unnormalized proposal. And these weights tell me how important a certain value chosen under G is with respect to my actual target pi. And what we can then do is employ self-normalized importance sampling estimators to estimate my theta, which is, in this case, is just going to be the sample average, except weighted by the normalized weights. And so this weighting is then basically going to correct for the mismatch between the fact that I actually got samples from G, but I wanted to estimate expectations under pi. Okay. Now, importance sampling is fairly well studied for when your YTs are IID samples. So when you're able to get IID samples from G. And one of the reasons or main historical motivations for importance sampling has always been that I can actually do significantly better than Monte Carlo, good old-fashioned Monte Carlo, if I use my importance, if I identify my importance sampling density well enough. So the variance of the importance sampling estimator can be smaller than the variance of the sample mean from just regular Monte Carlo. So if I could highlight some instances of this. So for example, again, if my target density is the Gaussian target density, and I employ an importance proposal of G to be normal 0,2, then under at least IID sampling, provably variance of the importance sampling estimator is going to be smaller than the variance of a good old-fashioned Monte Carlo. And one of the reasons this works is because, well, A, the mode of G matches the mode of pi, my target. So there's a mode matching. And the other reason this works is that, if you can see, is that the tails of G are always sort of fatter or enveloping the tails of pi. And so once this happens, these two features happen, it's sort of relatively likely that we'd have a relatively more effective importance sampling strategy. So I can also show some instances of when this doesn't work. So for example, when I have my target density to be Gaussian, and my proposal is normal 0,1/3, so it's like 0.33. In this case, my variance of the importance sampling estimator is going to be infinite. And also in this case, when I don't get the mode right, and I'm not able to set the proposal at the same mode as my target, then I have a similar issue. And in both of these instances, actually, the issue is the fact that tail behavior is a problem. So in this first curve, I see that the tail, the pi envelopes G in the tails and not the other way around. And in this case as well, on the left-hand side of the plot, I see again the pi envelopes G in the tails and not the other way around. And this is really the issue in finding good importance sampling strategies, because what we'd like to do is find a density that is able to envelope things in the tails of the distribution. And this is fairly challenging in high dimensions. And this is what we're going to try and tackle using Moreau-Yosida envelopes. Okay, so I'm going to move on to talking about Moreau-Yosida envelopes at this point. But sort of the overarching focus is going to be on employing, on sort of marrying ideas from importance sampling and gradient-based proposals. Okay, so what are Moreau-Yosida envelopes? So first, I'm going to define my class again. So I'm assuming psi is convex and lower semi-continuous. And pi of x is proportional to e to the power minus psi of x. So this is the same class as before. And again, I'm fixing psi to be convex. Then the Moreau-Yosida envelope for a given lambda greater than 0 of this function psi of x is defined as psi lambda x, which is the infimum over my Euclidean space of psi of y plus 1 minus 2 lambda L2 norm squared between x and y. Now, the first time I saw this, I didn't quite understand what this was. So what helped me personally was trying to visualize this for a Laplace target density. So if I consider pi of x to be proportional to e to the power minus absolute value of x, I'm going to try and motivate what this Moreau-Yosida envelope looks like for just this example. And then hopefully psi lambda x would make a little bit more sense. So this is what I do. And I'm going to plot here in the black curve is psi of x. So this is just absolute value of x, right? This is a convex function. And what I'm going to do is, for example, here, I'm drawing what's inside of these parentheses, what's inside of this infimum statement for various values of y. Okay, so at y equals -2, for example, as a function of x, this is nothing but a quadratic function of x. Right? It's because I just have a quadratic term over here. So it's just a quadratic function of x whose minimum happens at psi of y, and I've chosen y to be -2. So minimum happens at this point. So it's a parabola that shifted up to that point and moved y units in this direction. Right? So it's just a parabola that's moved up and shifted appropriately. And then I can do the same thing at various values of y. So I do the same thing at various values of y. So at y equals 0.5, I have a parabola that obtains its minima at psi of y, and it's shifted y units onto the right-hand side, right? And I can fill this whole space. But then what I'm going to try and do is for every value of x, I'm trying to find the smallest, I'm trying to find the smallest value that these blue curves can take, right? So for example, at -2, the smallest value that these blue curves can take is this value over here, right? And so in this way, it's the smallest value is just going to be the line that's going to be joining each of these blue boundaries, so to say. And so the psi lambda x is going to be that pointwise infimum. Oops. Yeah, which is going to look something like this red curve over here, which is then going to be my psi lambda x. In this example, psi lambda x turns out to be the popular Huber loss function. Okay. But then what's very interesting, you can notice psi lambda x is actually always below psi of x. And this is really the feature we're going to be employing, is now that I have a psi lambda x, I can actually exponentiate it and generate or write it down as pi lambda x proportional to e to the power minus psi lambda x. So for example, I have lambda equals 0 actually corresponds to my original psi of x. And I have the corresponding pi lambda x, which is just the Laplace density. And now I can basically keep changing this for different values of lambda. So this is lambda equals 2, and then this is pi of lambda for lambda equals 2. Okay? And similarly, and so what you see happening is that as lambda is increasing, I'm getting a pi lambda x that's becoming flatter and flatter, and it's sort of enveloping in the tails. And that's really what we're going to be highlighting. So the key properties of pi lambda x, which were highlighted together in Dermis et al. 22 and Marcela Pereira's paper from 2016, is that pi lambda x is actually a valid density for all lambda. So for us, this means that we can sample from it. When psi lambda x is actually going to be convex as well and shares minimizers with psi of x. Now, this tells me that this can make for a good importance proposal because I will have mode matching then. I also know that pi lambda envelopes phi in the tails, and this will then imply that it'll be a good importance proposal again because I'll have good features in the tails of the distribution. And then most importantly, provably psi lambda x is actually differentiable, it's smooth, and gradient Lipschitz, which means that I can actually use and employ gradient-based MCMC methods to sample from psi lambda x. Right? So these are like the 4 properties that are going to help us build our intuition for building our important sampling strategies. Now, the pi lambda x and in general, the space has been, the Moreau-Yosida envelopes have been employed definitely many a times before. So one of the first papers that I did in a complete way was Marcela Pereira's paper, where for non-differentiable targets, they replaced the gradient of psi of x with the gradient of psi lambda x in just the Mala proposal, and then did accept reject with the correct target density, right? So this is an exact Markov chain that's employing gradients from psi lambda, not psi. And a similar thing was then done by Chari et al. To build an HMC version, where it's the correct target density with respect to which the accept reject is happening, but the gradients are being used from psi lambda, the approximation. And then Durmas et al. Did like a unadjusted Langevin method, where they ran an unadjusted Langevin algorithm replacing the gradients of psi with the gradients of psi lambda. Right? We focus on sort of comparing our methods to P-Mala and P-HMC because these are exact implementations similar to ours. Okay, so what is our strategy going to be? Well, now that we've understood Moreau-Yosida envelopes can be quite useful, we are going to implement MCMC importance sampling using these Moreau-Yosida envelopes. So the first thing we do is we fix a lambda greater than 0, and I'll come back to what this lambda will be later or can be later. And then what we do is say, well, you run your choice of gradient-based MCMC method that's invariant for pi lambda, not pi. Right? So once you fix your lambda, you look at your approximation pi lambda, and you choose your favorite gradient-based method there. Now, the good news is that pi lambda is going to be smooth and will be gradient Lipschitz as well. So a large class of these algorithms can work fairly well. And then I have the form of the gradient as well. I have gradient of psi lambda x, which is x minus the proximal mapping of psi lambda at x divided by lambda. And the proximal mapping is nothing but the argument where the minimization is happening in the Moreau-Yosida calculations. So this is really the thing that brings in the lambda part, is that we're using this particular proximal mapping. And that's it. Once I have my samples, these are unfortunately from pi lambda, not pi. And so what we can do is then we can correct for the mismatch between pi and pi lambda by constructing these self-normalized importance sampling adjustments, which is what we finally call as theta hat my sub n, my standing for Moreau-Yosida. So our final estimator of theta then is theta hat n my. Okay. Now, a pro immediately is this can be used for non-differentiable targets as well as targets that have very thin tails and have not reliable gradients in the tails. But then naturally in any importance sampling paradigm, a good question to ask is what happens to the variance of my estimator? Can we say anything? Can I trust this estimator at all? So I'm going to focus on some of this in the next part of the talk. So that's the first thing we look at is what is the variance of the estimator, and we do this by establishing asymptotic normality of our Moreau-Yosida estimator. So let XT be a pi lambda ergodic Markov chain, and I am assuming I forgot to write that I'm assuming reversibility over here. So because I'm employing Metropolis Hastings samplers, but let XT be a reversible pi lambda ergodic Markov chain that is geometrically ergodic, and that I have two moments under pi, right? Then as n tends to infinity, I have asymptotic normality of the importance sampling estimator with a limiting covariance matrix of chi. Now chi takes a specific form, and I'll come back to the expression later on. But just something to keep in mind is that what we need to do is track the tuple x w lambda and w lambda being our weights from pi and pi lambda. And the result basically follows by calling at a Markov chain central limit theorem for this particular tuple, which gives me this infinite sum of lag covariances for sigma. And then I use a delta method argument to get the final expression for the limiting variance covariance chi. And I'm going to come back to this expression in more detail later, but really the proof for the importance sampling part relies on the fact that provably w lambda x is bounded above by 1. And so that means I have things that remain stable in the weights, in the tails of the distribution. Okay. A natural question. So one of the assumptions is that the Markov chain, we're assuming, is geometrically ergodic. So a good part of the paper then focuses on what kind of results can we say about pi lambda. And so this becomes not so tricky to look into, because there's a fairly large amount of literature out there that establishes geometric ergodicity of Mala and HMC. And so these are the two algorithms we focus on, except we run Mala for pi lambda, and we run HMC for pi lambda. But pi lambda, we know, takes a specific form in the sense that it is a Moreau-Yosida constructed density approximation. So what we can do is we can rely on the results of Roberts and Tweedy, which study sufficient conditions for geometric ergodicity for Mala, and Livingstone et al. That considers sufficient conditions for geometric ergodicity for HMC, to study when are these conditions true for pi lambda. So we have general results as well, but here I just focus, to keep things simple, I just focus on the following family of target densities. So if my target density is in the family that pi of x is proportional to e to the power minus some scaling factor gamma, but x to the power beta. So for example, when beta is 2, this is the Gaussian density. For beta is 4, this is the super Gaussian that I had shown. Well, then if beta is between 1 and 2, then pi Mala and pi HMC that target this pi are both geometrically ergodic. And then pi lambda, which is the Moreau-Yosida approximate density for this pi, if I run pi lambda Mala and pi lambda HMC, those are also then geometrically ergodic. So that these are the results we show. And when beta is 2, all of these algorithms are geometrically ergodic if we tune these proposals reasonably well. But then when beta is greater than 2, provably pi Mala and pi HMC are not geometrically ergodic, but pi lambda Mala and pi lambda HMC become much more structured in the tails of the distribution. They become basically Gaussian-like tails, at which point these are geometrically ergodic if tuned properly. So for this particular family, we sort of highlight these results. And that's the takeaway, that for when pi has thin tails, pi lambda has Gaussian tails, which then does yield geometric ergodicity. Okay. And so I'm skipping some things in the talk. These can be found in fair amount of detail in the paper, but we have general conditions as well for when pi lambda Mala and pi lambda HMC are geometrically ergodic. And these are essentially adaptations or sort of carefully studying the conditions from Roberts and Tweedy and Livingstone et al. Now, in any sort of Bayesian inference problem, it's not just the posterior means and expectations that are of interest. So we also use the work of Chen and Xiao to construct and build quantiles in an effort to maybe make credible intervals. And I only focus on expectations of just the posterior mean, but naturally this can be extended to any function chi of interest. And then the asymptotic variance covariance matrix can actually fairly easily be estimated using all the work that that's available in Monte Carlo variance estimations, because there's a parametric form available for that. Okay, but a key part of what I've skipped is at every point I said let's fix lambda, but now we actually have to focus on how do I actually fix lambda. And so there's certain guidelines or results we follow to build some intuition and heuristics for this. So the first thing we look at is, well, what happens if my target density is Gaussian? Now, obviously Gaussian is a well-behaved target, but just to build some intuition. So when pi is the Gaussian density, then the my envelope density, pi lambda, is basically a better conditioned version of a Gaussian. So it's a Gaussian with covariance omega plus a diagonal element of lambdas in there. So there's going to be a lambda factor benefit in the conditioning of the target distribution, which then gives us the intuition that our underlying Markov chains would then be able to sample from pi lambda probably better than they would be able to sample from pi, especially if we're not doing any preconditioning in our sampler. And then here's something else that helps us. So if I look at the eigenvalues of omega for this target, so if I order the eigenvalues from D1 up to DP, and then if I'm getting IID samples, so this is only for IID samples, and if I'm estimating the mean of this distribution, then the lambda that minimizes the asymptotic variance is solved this particular equation, which is not very interesting, but we were able to show is that the optimal lambda that minimizes it lies between D1 by P and DP by P, which basically means that it's bounded above and below by the largest eigenvalue, smallest eigenvalue divided by the dimension, largest eigenvalue divided by the dimension, which then says that optimal lambda scales linearly with dimension, right? And that gives us, again, an intuition that sort of makes sense. As our dimensions are increasing, our weights are going to be smaller and smaller, and then and that's going to happen at linearly as a function of dimension. So these are the takeaways. Is pi lambda is hopefully better condition that's going to encourage better mixing, which then implies the following, that if I want to choose lambda to give me small variances, I then have to look at the asymptotic variance expression that I have. So first I claim is I want to choose lambda so that I have smaller variances. Now my asymptotic expression for the variance has a couple of different terms. This first term is coming purely because of the importance sampling paradigm that we've opted. So because this is the square of the first moment of the weights. And the sigma over here is coming because of the MCMC that we have opted. So this has the MCMC correlation. And then the IP minus theta is because of the delta method. And that is just a part of the problem, right? So theta is something that we want to estimate. So as we change the theta that we want to estimate, the variability is going to be changed by these two factors. So it's basically the red term in the weights and the sigma that's impacted by the choice of lambda. Now, what's going to happen is as lambda is going to increase, if we go by the intuition set forth in the first line, as lambda increases, pi lambda becomes better conditioned, which improves the mixing of the chain, which then will reduce sigma, right? It will reduce the correlation structure in the chain. And then as lambda is increasing, the other thing that will happen is pi and pi lambda will increasingly become farther and farther from each other, because my pi lambda gets flatter and flatter. But that will make the weights to decrease. And if the weights decrease too much, then this is going to increase, is going to lead in a massive increase in the variance. So this is like the trade-off that we want to balance, is if I want a really effective Markov chain, I might want to employ a much larger lambda, but that's going to come at a cost of reduced weights. And there's somewhere in the middle, there's an optimal lambda. We try to look at whether we can formulate what is a value of the optimal lambda, but because this sigma over here has, your Markov chain limiting variance hidden in here, it becomes quite difficult to characterize what is an optimal lambda. But we can give some guidelines, and the guidelines are the following, is that we can then go by the following principle, that how about we increase lambda until the weights are just too small? Because increasing lambda is going to improve mixing, is going to increasingly keep on improving mixing, but you don't want to have lambda too much. And so you can basically track the weights and ensure that until the weights are too small, I can keep increasing lambda. But then when do I know that the weights are too small? Well, we can employ some of the heuristics that are available in the importance sampling literature via the importance sampling effective sample size, which basically tries to quantify the second moment and variability of the weights. So Kong's work in 1992 describes the importance sampling effective sample size, NE, as such that NE by N is the square of the first moment of the weights divided by the square of the second moment of the weights in an effort to measure variability. And what we then heuristically find is that an optimal value of lambda is obtained so that one chooses lambda so that NE by N, this effective sample size factor is between 0.4 and 0.8. Now, this is purely by understanding for various examples, what does this usually look like? We would love to be able to characterize sigma over here in such a way that we can actually obtain an expression for an optimal lambda, but that seems quite difficult at the moment. Okay, so let's actually see whether this principle of choosing lambda in this sense, in this way, makes any sense. So what we do is I take the Laplace distribution, but I take it in 20 dimensions. And what I'm going to plot over here is the important sampling effective sample size. So this is going to be NE by N. And then I'm going to plot the effective sample size of just the Markov chain, which is a different effective sample size, which measures the mixing, or it tries to measure how well the Markov chain is exploring the space, and how well the Markov chain is estimating the mean of its distribution. And then I also look at capital Chi, which is the limiting variance in this problem. And so here's what happens. As a function of lambda, we choose various lambda, and then I look at NE by N. So I look at the first plot, which is the important sampling effective sample size, and I see that this decreases down and continues to decrease down as lambda increases, which makes sense because pi lambda is increasingly becoming more and more different from pi. And my vertical lines are the values of lambda at which I get NE by N to be equal to 0.4 and 0.8. So this is where this is 0.4 and this is where this is 0.8. So these are sort of like the nice values of lambda that I have found. Now I see that the pi lambda ESS, the mixing of the Markov chain, continues to improve as I increase lambda. So as I increase lambda, the mixing gets better and better. And that's measured here. And what you note is that the asymptotic variance in this case is sort of minimized right around in this area of the optimal value of lambda. But what's more important, I think, to view in this plot is that notice that when lambda is 0, this is the asymptotic variance, which corresponds to running not doing any important sampling, right? And for any choice of lambda from here to here, in this problem, you are going to get variance reduction in this problem, right? So that's really one of the takeaways. Of course, the window is interesting, but it's also that any of these choices would have been better. Okay, this is a toy problem. We have another one in this case where it's e to the power minus x to the power 4 in 20 dimensions. And here, again, the weights decrease. And then these are the values of lambda at which we get the behavior that the weights are in this window. I get pi lambda ESS is still increasing. But then over here, I see that because this is a very quickly diminishing tail distribution, these choices of lambda would have been too big, and it prefers definitely smaller choices of lambda. It doesn't want to pick up too many bigger choices of lambda. Those were toy examples, and I'm going to show a Bayesian L1 trend filtering example. And so the idea here is that I have a bunch of one-dimensional data that I've observed that are indexed by time. And currently they form, if I just plot the y's, which is my observation, then I plot it like this. What I want to do is to be able to find a trend just as a function of time. Okay, so there's no other explanatory variables. I don't even have year or months, etc. I just have an index as a function of time. And what we employ here is a Bayesian model, which is a Bayesian L1 trend filtering model that essentially imposes the type of trend that we want to see. So the L1 part is going to impose either constant trends, linear trends, quadratic trends, or cubic trends using a sparse characterization. So the psi of beta, so recall that psi represents the convex function in our log concave density. So psi of beta in this is basically the square deviation between y, my observed data, and beta, which is what I want to estimate. But of course, if this is what I try to minimize, then my curve that I get is just going to to connect all the dots, and I'm not going to actually be able to find any trends, because this y minus beta, if I minimize over my parameter space of all betas, it's just going to join on the dots. So what one does is one penalizes a certain matrix difference discrete operator times beta that is then going to induce a certain trend structure because of the L1 norm here. So in this case, for example, we use a k plus 1 discrete difference operator where, for example, k equals 0, this is going to induce a constant trend. And for k equals 1, that's going to induce a linear trend. And this is where the penalization comes in. So this is encoded as part of a prior, and this is encoded as part of a likelihood. Okay. Now, for this problem, what we're going to do is the following: that for that log target, we will run first to show you the effectiveness of sampling from pi lambda MCMC and proximal MCMC. So we run one Markov chain that's going to sample pi lambda, and we run another Markov chain that samples the actual pi, but uses proximal mappings because this is not really differentiable. And our choice of lambda was 0.001, and NE by N for this choice of lambda was about 0.45. This is a 100-dimensional problem. And both samplers were run for 100,000 samples. And here, this is just an effort to show what is the quality of mixing in the two samplers. So this is like the difference in the ACF plots. Bear in mind, these are two completely different targets. So I'm sort of comparing apples to oranges, but because these are autocorrelations, I can sort of compare them. So this is pi lambda mala and p mala. And if I look at the difference between them, I see that there's not much different or significant difference across the lags. The pi lambda mala is almost just a marginally better than p mala of Pereira, Pereira's work that uses proximal mala. But actually in HMC, we find that the HMC that targets pi lambda is far more effective, and I see massive negative differences in ACF. So negative differences means that the ACF by pi lambda HMC is smaller than the ACF by p HMC. So this indicates that the HMC sampler mixes very well on pi lambda, but the mala sampler is equally bad or good mixing for both the targets. But this is why I've chosen this example to show is I have an instance where the Markov chain isn't very good necessarily on pi lambda, but this Markov chain is very good. But then if I assess the overall efficiency, if I look at the variance of proximal MCMC divided by the variance of the Moreau-Yosida importance sampling estimator to see how well I am doing in estimating the quantities I want to estimate, well, the relative efficiency of mala, even for the worst component, is at least 2.6 times better than running proximal mala on pi itself. And this is when the Markov chains themselves are not necessarily any better. And this is almost purely a function of the improvement caused by importance sampling. But then if you also bring in an effective sampler like HMC in this case, then I get even the worst mixing component gives me a relatively better efficiency, almost as a factor of 20. So it's about 20 times more efficient overall when you do the pi lambda and you also do the importance sampling. Okay, I'm sort of ready to wind down. So just to also note, because one can use the work of Chen and Shao to also do quantile estimation. So from the importance sampling, we can also make like a credible band around pointwise around each posterior, marginal posterior in this particular way. Okay, so there are other examples. So for example, there are some other toy examples justifying the choice of lambda by changing dimensions as well. We have another non-differentiable example that is a large matrix denoising problem. This is in about 4,000 dimensions. And then we have an example where the tails of the distributions are light. And so this is a differentiable target, but it's not gradient Lipschitz. And this is a Bayesian Poisson random effects model. And just to finish things off, just highlighting some pros and cons. So a currently a sort of significant con is that we focus on pi being log concave. Now, this is sort of our first hack in this line of work, and Eric and I have been discussing extensions to this, and this is something we're going to keep on really focused on working on in the next couple of months. Another con is naturally, and this is a con in this whole space of proximal algorithms possibly, is just the availability of psi lambda, which I haven't really talked about. Psi lambda requires calculating a proximal mapping, which may or may not be always available to us, and certainly not, sometimes not available cheaply. But there are a large number of proximal algorithms that are available, and a lot of these are coded in different packages, and also particularly for these kind of non-differentiable and diffuse sort of sparse priors that are well studied from the frequentist literature. There's a lot of algorithms available. But still, this does require some extra time. Some pros that I've sort of already highlighted is that one, I mean, certainly we would love for the asymptotic variance to be far more improved, but at the very least, we're guaranteed finite variances, which is something that's not always obvious in an important sampling paradigm. And then if you empirically tune lambda as well, based on some of the guidelines we've suggested, then you can get massive gains, as we've seen in some of our examples. And also, the efficiency calculations that we did are can be done in a very straightforward way, because we have a characterization of the asymptotic variance that helps the user do all the nice things they want to do in terms of assessing Monte Carlo variance. And something sort of tangentially from this, but I've been thinking about and working with a student and a collaborator, is we realized that if I want to do sort of marginal density estimation from important sampling after important sampling, I would like to do some quick KDE implementations, but there doesn't seem to be much out there. So if I want to do KDEs for marginals using important sampling, there's sort of obvious things I can do, but they don't seem to be very well studied. So this is something that I'm sort of interested in right now. But thank you so much. The work itself is been on archive for a couple of months now. If there's time for questions, I'm happy to take questions, or folks can email me as well.
Yeah, thanks a lot, Dootika, for the very nice talk, and it's very interesting. So I think now it's a good time to ask a question from both the audience and the panelists.